The other way we can deal with non-ideal behavior, so we've talked about it now for gases, and we use fugacity for that, is activity. And this is a similar concept, but now for solutions instead of for gases. And so if you remember when we were talking about mixtures, we derived this expression that the chemical potential of a solution, and now we're looking at chemical potentials instead of Gibbs energy because we need to think about partial molar quantities. So this is like the partial molar Gibbs energy for a solution. We showed that that is equal to the chemical potential of the pure substance plus RT log Pj over Pj star, right? So it's related to what's the partial pressure divided by the vapor pressure of the pure gas. So thinking about this solution. Now, the nice thing is we still have a similar sort of expression, right? We have some constant value here multiplied by RT log of something, right? In this case, it's Pj over Pj star. And if you remember, for an ideal solution that behaves according to Raoult's law, we can say that, okay, Pj is equal to the xj times Pj star. And then we can substitute that into this expression. And we'll get RT log xj, right? So we get an expression that depends on a concentration, right? In this case, it's the mole fraction. Now, if we don't have ideal behavior, we'll have some other expression. So kind of like how we can use the ideal gas law. In contrast, we would have something like the van der Waals equation or the Redlich-Kwong equation or whatever. For a non-ideal solution, we're going to have our Pj is going to be some other function. It'll often look like Raoult's law with some extra terms added, right? So it's multiplied by some exponential of alpha something squared plus some thing up here. It's some big expression up here, and we're not going to go into the details of looking at specific examples of this. But what we'd like is some function that can take, just like we did for fugacity, right? It takes all the non-ideal behavior and we sort of but incorporate it into just a single entity, a single variable that we can use to define our solutions. And so what we do for a solution is we define something called an activity, such that the chemical potential of our solution is equal to the chemical potential of the pure substance plus RT times the natural log of the activity. So that's this A here. So A sub J is the activity of component J. And it's just like a fugacity, it sort of combines all the non-ideal behavior into it. Okay, so what's sort of so with fugacities, we had the limiting behavior that as the pressure approached zero, it would behave ideally. And so what we want for our solutions is, what's the limiting behavior for activities? Well, the activity should approach the mole fraction and behave like an ideal solution as the mole fraction goes to 1. And right as we get to a pure substance, so to get this behavior, then we have to have the activity is equal to Pj over Pj star, right? So it's equal to this expression that we had up here. Let me put that even in a different color. So, right, because if you compare this equation up here and our version with activity here, these two things are equivalent. I'll circle it in the same color, right? Activity has to be equal to this, Pj star. Okay, so that gives us a way to define activity. All right, and similar to fugacity, we define an activity coefficient that's a ratio, similar to the fugacity coefficient of our activity compared to what the ideal would be, mole fraction in this case. And this is what we call the activity coefficient. Now, we will see that activity coefficients can be defined in different ways as well. Activity is not quite as straightforward as the fugacity, because what we can do is we can find this in terms of different units depending on what we're looking at. And so we'll be looking at that when we talk about solid liquid solutions.